In this video, we're going to derive the geodesics for the Schwarzschild geometry. These are the paths that massive objects and light beams will take in the curved spacetime near a spherically symmetric, electrically neutral, non-rotating body. So basically, this is how the gravity of planets, stars, and black holes affect light and mass. We're going to see some gravitational effects that don't happen in Newtonian gravity and are unique to general relativity, like gravitational lensing of light around massive bodies and the perihelion shift in the orbit of massive bodies, like Mercury's orbit around the Sun. These were both early tests of the accuracy of general relativity after it was proposed by Einstein. So in this video, I'm going to give a quick review of geodesics, then review gravitational orbits in Newtonian spacetime, then derive Schwarzschild geodesics, then compare the orbits of bodies in Newtonian gravity and general relativity, which includes discussion of how gravity affects light and also the perihelion shift of orbits. You can feel free to look at the video timestamps and skip ahead if you want. So now I'll give a quick review of geodesics based on what I said in Relativity 105F. A massive particle's world line through spacetime can be parametrized by its proper time tau. The tangent vectors with respect to tau are the particle's four-velocity vectors u. The four-velocity is a timelike vector, meaning its squared length is always positive, and it always lives inside the light cone because massive objects can't travel faster than light. The rate of change of the four-velocity vector with respect to proper time tau is the particle's four-acceleration vector a. The four-acceleration is a space-like vector, meaning its squared length is always negative, and it always lives outside the light cone. The square root of the negative squared length of the four-acceleration vector is the particle's proper acceleration alpha. This is the number that the particle would measure on an accelerometer that it's carrying along with it. A particle with no forces acting on it has a zero four-acceleration vector, and it follows a path through spacetime called a geodesic, which is sort of like the straightest possible path through spacetime. In general relativity, gravity is just the natural motion of objects traveling along geodesics through a curved spacetime. An object orbiting a planet, or freely falling down towards the planet, will both measure no proper acceleration on their accelerometers. So these are traveling along geodesics in spacetime. An object that's in deep space firing its rockets, or an object that's sitting on a planet's surface, would both have a non-zero reading on an accelerometer. These objects are not traveling along a geodesic. The object in deep space with rockets firing has a four-acceleration vector that's pulling it away from a geodesic path. And the object sitting on the planet's surface has the molecular forces of the planet's particles forcing it upward, away from a geodesic that would normally pull it towards the planet's center. So setting an object's four-acceleration vector equal to 0 gives us the geodesic equation, which can be written in several different ways. Solving the geodesic equation gives us the paths of freely falling particles through spacetime that are only affected by gravity and no other forces. Now, light beams are massless and always have a proper time of 0 by definition, so we can't define a four-velocity vector or four-acceleration vector for light. Instead, we parameterize light-like paths by a generic path parameter lambda, which gives tangent vectors d by d lambda along the light world lines. These tangent vectors always live directly on the light cone, so they are called light-like vectors, or null vectors, because their squared length is 0. A light-like geodesic is a geodesic where every tangent vector along the path is light-like, so the rate of change of these tangent vectors is 0. This gives us another geodesic equation that's parameterized with a generic path parameter lambda instead of proper time tau. It turns out that using a generic path parameter lambda instead of proper time tau gives us a geodesic equation that works for both massive particles and massless light beams. So massive particles follow geodesics with time-like tangent vectors, and massless light beams follow geodesics with light-like or null tangent vectors. But both light and massive objects obey the same geodesic equation. Our goal for this video will be to take the geodesic equation and use it to solve for the paths of massive particles and massless light beams through Schwarzschild spacetime, where the curved spacetime is caused by a spherically symmetric, non-rotating, uncharged mass. Before we look at geodesics in general relativity, let's do a quick review of gravitational orbits in Newtonian gravity. Let's say we're looking at the coordinates of a planet orbiting a star, using the 2D polar coordinates r and phi. The planet's position vector is capital R, and its velocity vector is d capital R by dt, where t is the universal Newtonian time coordinate. The basis vectors for this coordinate system, er and e phi, are just the partial derivatives of the position vector with respect to r and phi. Using multivariable chain rule, we can expand the velocity vector in terms of the radial coordinate r and the angular coordinate phi. And here I'm going to denote time derivatives using an overhead dot above the variable. And the derivatives of the position vector with respect to the coordinate variables give us the basis vectors er and e phi. The squared magnitude of the velocity vector is just the dot product of the velocity vector with itself. Using the metric for polar coordinates, where er has length 1, er and e phi are orthogonal, and e phi has length r, so this dot product gives r squared, we get this formula for the squared velocity magnitude. We know that this planet's angular momentum vector L is just the cross product between its position vector capital R and its linear momentum p, which is mass times its velocity vector. If we sub in our formulas for the position and velocity vectors and distribute over the cross product, we know that the cross product of a vector with itself is 0. So er cross er is 0, and the cross product of er and e phi is a vector perpendicular to them both, whose length is equal to the area of the parallelogram formed by er and e phi. This area is 1 times r, since e phi has length r, and the perpendicular vector is ez. So the radial velocity doesn't contribute to angular momentum. Only the angular velocity does. And rearranging, we see that the magnitude of the angular momentum L over mr squared equals phi dot. We know the total energy of the orbiting planet is just its kinetic energy, 1/2 mv squared, plus the potential energy, which is mass times the gravitational potential function v of r. In previous videos, I wrote the potential as phi, but in this video, I'm going to write it as v. We can sub in our formula for velocity squared, then distribute 1/2 m, then sub in our formula for phi dot, then do some canceling. We can also use the standard Newtonian potential for a mass capital M, which is negative g capital M over r. Now, we see that in polar coordinates, kinetic energy actually depends on the r coordinate position. We can group this r-dependent kinetic energy term together with the r-dependent potential term, and called the combined terms the effective potential, v sub f. This is our main equation of motion for gravitational orbits in Newtonian gravity, where E is the constant total energy and L is the constant angular momentum. Technically speaking, these two terms give kinetic energy, and this term gives potential energy. But in this video, I'm going to treat this term as the effective kinetic energy because it depends on r dot. And I'll call these two terms the effective potential energy because they depend on r. For now, we're going to put this equation aside and derive the geodesics in our new theory of gravity, general relativity. We're going to find that the equation describing the orbit in general relativity is nearly the exact same as in Newtonian gravity, but with some slight changes. So our geodesic equation is actually 4 separate equations, one for each spacetime coordinate. This sigma index can refer to any of the 4 spacetime variables, ct, r, theta, and phi. To make our lives easier, we're going to assume our geodesics have a constant theta value of theta equals pi over 2, meaning the orbit is in the plane of the equator in our coordinate system, and all theta derivatives go to 0. We're allowed to make this assumption because our central mass is spherically symmetric, and we can always rotate our coordinate system so the orbit is in the plane of theta equals pi over 2. Now, in Relativity 108a, I wrote out the Schwarzschild metric in terms of 2 functions, a of r and b of r. And then we determined that a equals 1 minus rs over r, where rs is the Schwarzschild radius, and b is 1 over a, which can be written as r over r minus rs. If we calculate the derivatives of a and b, we can sub them in to get formulas for the connection coefficients TTR, RTT, RRR, as well as R theta theta and R phi phi. So we now know all 9 non-zero connection coefficients for the Schwarzschild metric, written as explicit functions of r and theta. Now, you'll notice that our Schwarzschild metric only depends on r and theta, but doesn't depend on time or phi. This is a hint that there are conserved quantities associated with the time and phi variables. A more technical discussion of this involves killing vectors, but I won't discuss that in this video. So our time and phi geodesic equations will give us conserved quantities. The r geodesic equation will give us an equation for tracking the orbiting body's radial distance. And because we're using a constant theta equals pi over 2 coordinate, the theta geodesic equation just becomes 0 equals 0. Let's start with the time geodesic equation. To write out this summation over mu and nu, we need to find all the connection coefficients with t on top. There are only 2 connection coefficients with t on top, which are the TTR and TRT connection coefficients. And they both equal each other, so I'm just going to write this sum as 2 times gamma TTR, matching t with a time derivative and r with an r derivative. And we can replace the TTR coefficients with this, and then cancel the 2 and 1/2. We can show that this equation tells us that this quantity, the derivative of ct times 1 minus rs over r, is a constant of motion that doesn't change along geodesics. To see this, let's take the derivative of this quantity. We use product rule and get the derivative of the derivative in the first term, and the derivative of 1 minus rs over r in the second term. The derivative of 1 is 0, and we can use power rule on the derivative of r to the negative 1 to get r to the negative 2 with a minus 1 in front, times a chain rule term. These negative signs cancel, and if we write this 1 as r over r, we get an equation that's equivalent to the right-hand side of our time geodesic equation, which equals 0. So if this equals 0, we just multiply by the reciprocal of this term, cancel r, and we get our original geodesic equation. So since the derivative of this term equals 0, it is a constant quantity along geodesics. This constant is sort of like the energy per unit mass, which we will denote by curly E. If we look at this constant of motion very far away from the mass as r approaches infinity, and rewrite dt by d tau as gamma, and multiply by mass, we see that this value is the time component of the 4-momentum vector from special relativity. So this is one reason why we refer to this constant of motion as energy. For the r geodesic equation, we get 4 connection coefficients with r on top. And since theta is constant, the theta derivative goes to 0. If we plug everything in, this sine theta goes to 1, but we still get a pretty complicated equation. We're actually not going to worry about this equation in this video. For the theta geodesic equation, there are 3 connection coefficients with theta on top. And if we assume theta is a constant of pi over 2, with these derivatives being 0, this equation just becomes 0 equals 0. This is a good thing, because it tells us that a constant value of theta equals pi over 2 does not violate our geodesic equations. So it's acceptable to assume all geodesic motion happens in a flat plane. Finally, for the phi geodesic equation, there are 4 connection coefficients with phi on top. But since theta derivatives are 0, this last term goes to 0. So we just have this for our phi geodesic equation. This is associated with another constant of motion, which is r squared times the derivative of phi. If we take the derivative of this, apply product rule to both r squared and the derivative of phi, then here we use power rule to get 2r times a chain rule term. This result is equivalent to our original phi geodesic equation. We just take this to equal 0 and divide by r squared. The formula r squared times the derivative of phi is actually the same formula as the Newtonian angular momentum L per unit mass, which we will denote as curly L. This is a conserved quantity associated with translations in the phi coordinate, which are basically rotations. So it makes sense that it's the angular momentum. So we've found 2 constants of motion for our geodesics. But there's one more thing we need, which is an equation for the squared length of our tangent vector, which comes from the metric. Expanding the tangent vectors using multivariable chain rule, we get our standard metric formula for the squared length of a vector, which expands to 4 terms using our Schwarzschild metric. The theta derivative is 0, and plugging things in, this sine theta goes to 1. So we have a formula for the squared length of our geodesics tangent vectors. Notice that the derivative of ct also lives in our energy constant of motion. With some algebra, we can solve for the derivative of ct. The derivative of phi can also be solved for using our angular momentum constant of motion. We can now plug these in to get this. As a final step, we can set the squared length of our tangent vector equal to a number epsilon. This number is 0 for Lightlike Geodesics, and positive for Timelike Geodesics that massive bodies follow. We can then rewrite 1 minus rs over r as r minus rs all over r, and do some cancelling, and bring epsilon to the right-hand side. Then we can multiply all terms by r minus rs over r, leading to cancellations here and here. And we can again rewrite this as 1 minus rs over r. If we bring curly E to the other side of the equation and distribute, we find we get an equation that kind of looks like a total energy equation, involving a derivative of r for the kinetic energy and an effective potential term that only depends on r. And remember, the epsilon equals 0 case is for light, and the epsilon greater than 0 case is for massive bodies. Let's start with the massive body case. We can sub in the full formula for the Schwarzschild radius and use proper time tau as the path parameter. This means that epsilon is just the 4 velocity dotted with itself, which is the speed of light squared. Putting this all in, we can cancel c squared and then multiply all terms by 1/2. With a little more algebra, we can make this look more like the equation describing Newtonian orbits. We can replace curly L with angular momentum over mass, and replace curly E with energy over mass. Then multiply both sides of the equation by mass. Then move this constant 1/2 mc squared to the other side of the equation. If we now compare the equations for Newtonian orbits and orbits in general relativity, we see that both equations have a constant term on the left-hand side that's related to energy. The general relativity energy term looks more complicated, but the important thing is that it's constant. We also have an r derivative term that's like kinetic energy, and several terms that depend on r, which are like the effective potential. The Newtonian and general relativity effective potentials are the exact same, except for a term involving 1 over r cubed. This last term goes to 0 very quickly when r is large, but it can have a very large effect for small r. So the main differences between massive body orbits in Newtonian gravity and general relativity should only occur at small values of r, due to this new 1/r³ potential term. One way to understand these equations is to graph the effective potentials in each case. To simplify graphing the Newtonian potential, I'm going to assume all the masses and physical constants are equal to 1. We can then plot this function for different values of angular momentum L to get a sense of their basic shapes. Now let's focus on the L equals 0.5 case. We know that the total energy is constant, and the kinetic term and potential term can each get bigger or smaller, as long as their sum is a constant value. If we say this is the amount of total energy E in the system, we know that the orbiting body is going to be restricted to this region of the graph. The amount of potential energy can go up and down, but it can never exceed the amount of total energy. So a body with this amount of energy can't leave this potential well. The points where the constant energy line intersect the potential curve are the points where the total energy and potential energy are equal, meaning the kinetic energy must be 0. So the orbiting body will go back and forth in this potential well. This represents an elliptical orbit, where the radius reaches a maximum point, then turns around, then reaches a minimum point, then turns around again, with the radial velocity being 0 at the turning points. If instead the total energy line is exactly at the bottom of the potential well, then the potential energy and total energy are equal for all time. This means that the r dot term is 0 for all time, so the radius is constant for all time. This corresponds to a circular orbit with a constant radius. If the energy is very high, above the potential well, then the mass has too much energy to be caught in an orbit. So it just approaches the central mass, then leaves again and goes off to infinity, getting deflected by some angle. We can solve for the exact radius of circular orbits by setting the radius to be constant, so that the derivative of r, or r dot, is 0. This means that the constant total energy equals the effective potential energy, so V effective is constant, meaning its derivative is 0. If we take this derivative using power rule, cancel minus signs, multiply by r³, and cancel, we can solve for the radius of circular orbits in Newtonian gravity, L squared over m squared g big M. Now let's use this same graphing approach for the potential in general relativity. I'm going to replace the energy term on the left-hand side of the equation with curly E tilde to save space. Again, setting the masses and physical constants to 1, these are the potential curves for various values of curly L. We can see that there is a circular orbit right at this peak here, if we have the exact right amount of energy. But if we nudge this mass even a little, it will either fall towards the central mass or go off towards infinity. So this is an unstable circular orbit, because even a slight change to the energy will stop the body from orbiting altogether. Now, it's difficult to see on this graph, but there's actually a second circular orbit at this point here. This part of the potential graph actually forms a very shallow well, where circular and elliptical orbits can exist, just like in Newtonian gravity. So unlike Newtonian gravity, general relativity predicts 2 possible circular orbits for a given angular momentum. We can solve for the radii of these 2 circular orbits, assuming the orbit radius is constant, meaning the effective potential energy is constant and has 0 derivative. We use power rule on the rest of the terms, canceling these negatives and these 2's. Multiplying by r to the 4th and canceling, we get an equation that's quadratic in r, and can be solved using the quadratic formula. Subbing in, we get this solution for the 2 circular orbits, given by the plus and minus signs here. These give the locations of the two possible circular orbits in general relativity. The circular orbit closer to the mass is unstable, and changing the energy even a little will cause the body to stop orbiting. The second circular orbit that's farther away is a stable circular orbit. Changing the body's energy by a little bit will simply change the circular orbit into an elliptical orbit. Also, we can compare the circular orbits from general relativity to the circular orbit in Newtonian gravity. If we take the speed of light to approach infinity, this term goes to zero. After canceling and replacing script L with L over mass, we recover the expected circular orbit from Newtonian gravity. So this means that when we're dealing with small masses and slow speeds, Newtonian gravity is a very good approximation for general relativity. Now, as we tweak the script L constant of motion, there is a threshold where the unstable and stable circular orbits become the same. Mathematically, this is when the discriminant of the quadratic formula becomes zero. We can solve this point to be when curly L squared equals 12 gm over c all squared. Plugging this back in for curly L squared, and knowing the discriminant is zero, we get a critical radius of 6 masses times a physical constant, which is also equal to 3 Schwarzschild radii. This is the smallest possible stable orbit in general relativity. This distance is also called the innermost stable circular orbit, or ISCO. Now, if we want to look at the orbits for light, we can just take our original equation and set epsilon equal to 0, which reduces the effective potential to just 2 terms. We can again find circular orbits by forcing the r-coordinate to be constant, meaning the effective potential is constant, meaning its derivative is 0. We take this derivative using power rule, cancel negative signs, multiply the equation by r to the 4, and cancel. And we can solve for a circular orbit at 3 over 2 times the Schwarzschild radius, which is also 3 times the central mass capital M times a physical constant. This means that for a Schwarzschild black hole, if we turn on a flashlight sideways at exactly 1.5 times the radius of the event horizon, the light beam would orbit the black hole in a circular orbit. Because of this, the sphere with a radius of 1.5 Schwarzschild radii is called the photon sphere. If we graph the potential for the orbits of light, we can see the circular orbits appearing at 1.5 times the Schwarzschild radius for all values of curly L. But even outside this radius, the central mass will still impact the path of light beams, deflecting them somewhat from a straight path. The first evidence that light beams from distant stars were bending due to the sun's gravity was collected during a total solar eclipse on May 29, 1919, during the Eddington experiment, which was an early experimental confirmation of the predictions of general relativity. The last thing I'll cover in this video is another early experimental confirmation of general relativity, which is the perihelion shift of planetary orbits, specifically in the case of Mercury. Newtonian gravity tells us that planets orbit the Sun in elliptical orbits, where the perihelion is the smallest distance between the planet and the Sun. In general relativity, the extra 1 over r cubed potential term causes the perihelion to advance in the direction of orbit, resulting in a flower-like orbit shape. However, this effect is extremely tiny, and is usually only noticeable for small values of r over long periods of time. Perihelion advance in general relativity technically happens to all the planets in the solar system, but the effect is most obvious for Mercury since it's the closest to the Sun. To derive perihelion shift, the goal is to get the formula for the planet's orbit radius r in terms of the orbit angle phi. The mathematical derivation of this is a bit crazy, so I'm going to speed through it, and you can pause if you want to go through it more carefully. We start with our energy equation, then use the case for massive bodies. We can use single variable chain rule to rewrite dr by d tau as dr by d phi times d phi by d tau, which we can rewrite using our curly L constant of motion. Then we multiply by r squared over curly L squared, and change variables so that r equals 1 over u. This has the advantage of the derivative of r over r equaling the negative derivative of u over u. Then we multiply by u squared. We then differentiate both sides by phi and cancel du by d phi on all terms, multiply by this, and cancel the 2's. We can again change variables to w to absorb this constant, and we end up with this differential equation where alpha is this constant. On its own, the left-hand side of this differential equation equaling 0 is just the simple harmonic oscillator with a sinusoidal solution. If we include the constant 1 on the right-hand side, we get the equation for an ellipse, where this e value is the ellipse's eccentricity. The last term is the correction from general relativity, and corresponds to the 1 over r cubed term from the effective potential. We can write W as a power series in alpha. Subbing in, if we set the terms without alpha coefficients equal to each other, we get the original Newtonian differential equation for W0, which we know the solution to. If we set the terms with the first power of alpha equal to each other, we get this differential equation for W1. If we assume alpha is small, we can ignore the alpha squared and higher order terms. So the orbit solution is basically the Newtonian solution W0 plus a small perturbation involving W1. After squaring this and using trig identities to replace cosine squared with a double angle, this differential equation can be solved by assuming a solution of this form, with this constant and sinusoids multiplied by linear terms, with 4 unknowns. If we find the second derivative and add it to the original function, we get this. Matching this form with the original differential equation, we get that small a is the eccentricity, small b is 0, big B is negative 1 over 6 e squared, and big A's value doesn't matter, so we'll just take it to be 0. Putting W0 and W1 back into the power series, we notice this sine term multiplied by a linear factor, and this is the term that causes the advance of the perihelion. So we have an equation for W. Using the small angle approximation for sine and cosine, we can rewrite this using an angle difference trig identity, and see that this cosine term does not have a period of 2 pi. Instead, it has a period of 2 pi over 1 minus alpha. If we multiply this by 1 plus alpha over 1 plus alpha, and assume alpha squared goes to 0 since alpha is small, we find that, for a planet to complete one orbit and get back to the starting radius, it must cover an angle of 2 pi plus an advance of 2 pi times alpha, which is the advance of the perihelion. To calculate alpha for Mercury, we can easily get the Sun's Schwarzschild radius Rs from the Sun's mass. To get Mercury's angular momentum per unit mass, curly L, we can make the simplifying assumption that the angular momentum is the exact same as when Mercury has a perfectly elliptical orbit. Comparing the ellipse equation to the W0 formula we derived and setting the numerators equal to each other, we can calculate Mercury's curly L in terms of its orbit eccentricity E and the semi-major axis A, which gives this. Putting all this together, we get a perihelion advance of 2 pi times 8 times 10 to the negative 8 radians per orbit. Knowing Mercury's orbital period around the Sun to be 88 Earth days, we can calculate Mercury's perihelion advance in 1 Earth century, which is 0.0002085 radians, or 43 arcseconds. In reality, Mercury's perihelion shift per century is larger, due to the gravity of the other planets in the solar system. But 43 arcseconds is the amount of observed perihelion shift that cannot be explained by the gravity of the other planets. It's a small correction factor that general relativity was able to predict. So to summarize this video, we used the connection coefficients for the Schwarzschild metric to calculate the geodesic equations for the Schwarzschild metric for a constant value of theta equals pi over 2. The time and phi geodesic equations both gave us a constant of motion, and these let us turn the equation for the squared magnitude of a tangent vector into an equation that relates total energy, the derivative of the r coordinate, and an effective potential that depends on r. The main difference between Newtonian gravity and general relativity is this 1 over r cubed potential term. This term is negligible at large values of r, but causes non-Newtonian effects for small values of r, such as the existence of an extracircular orbit, a minimum innermost circular orbit, and the perihelion shift of elliptical orbits. General relativity also predicts that light rays will bend in the presence of mass, and can even orbit the mass along the photon sphere at a radius of 1.5 Schwarzschild radii. In the 108D video, we'll cover alternative coordinate systems for Schwarzschild geometry that will help make interpreting the geometry easier.